Alright, so where are we in this discussion? So we're talking about backpropagation of error. And so the way this works is you first take a forward pass through your network, and that's what we talked about earlier. In fact, that was the very first thing we did, right? Oops. Here it is. We took a forward pass through the data, and the idea is that there's pieces of information that we're filling in as we go. And so far we filled in the pre-state, the state, and the derivative of the state for each node in the forward pass. Okay, so these formulas give you how to do that. Good. Of course, you could do this node by node, like we were saying at the end of the video last time, but it's easier, I think, just to use the linear algebra to do it. And so we're going to try to do the linear algebra updates as well as the individual updates, just to give you the notation for both. Okay, so we're working on computing deltas in the network because the deltas are going to be used to compute the gradient for us. Okay, so in the backward pass then we started with the outer layer, and we got our deltas for the outer layer defined to just be the target minus the y. Remember, the y is what's being output here, so this is actually t minus s2, right? Good. So once we have computed the output layer, then we want to recursively compute the deltas in the remaining layers. And so this graph, I've been doing that a lot in these videos, right? I gotta stop doing that. I didn't notice until I started watching the video. Okay. Okay, I'll try not to do that. I don't think I do that in my lectures, but okay. So I've got these deltas here, and I want to compute the delta here. And so the way I do that is I went through this definition last time, so watch that video if you want to see that again. But what we're going to do is try to get the linear algebra version of this update. Okay. So I want to construct the change in L from this. And so off to the side here, I'm going to make a note about these sizes. What is the size of delta L plus 1? That's the number of nodes in layer L plus 1 by 1, right? And then the W L plus 1 is going to be the number of nodes. So this is a mapping from L to L plus 1. So that means L plus 1 by number of nodes in layer L, right? And somehow I want to combine these to get a vector in NL plus NL times 1, right? How am I going to do that? Well, one hint is you're moving backwards, right? And so while W maps NL space to NL plus 1 space, the transpose goes in the opposite direction. And so what we'll do is we'll take this W L plus 1 transpose and multiply it by delta on layer L plus 1. Now, we're keeping track of dimensions, right? So this is now NL by NL plus 1, and this is NL plus 1 by 1. And so therefore you get the right dimensions coming out, right? Good. But lastly, I don't want to forget my derivatives, so I need to element-wise multiply this vector by my derivatives on layer L. So let me say layer L derivatives. Good. And that gives me my matrix form of the update rule per layer. So given layer L plus 1, I can compute the deltas for layer L. Done. All right. So what am I going to do with all these deltas now that I've got them? By the way, you don't have to compute the deltas for layer 0. So when we're going through this, how many layers are you actually going to do for a 3-layer network? Well, you're going to compute the output layer, and then we just have one one of these. So that's not very much. But if we wanted to stick in another layer, we could, or another 10 layers we could, and yeah, we would be able to compute all of our deltas. All right. Now, define So again, at this stage, let me make a note of this. At this stage, all deltas have been computed. You could compute the deltas on layer 0, but we don't use them. So you could just set them equal to 1 if you wanted to. 1 or 0. Yeah. I better be careful about what I say. We may use them at some other time. So now we're going to let the change in Wijk be defined to be Sj k minus 1 times, now where are these coming from here? This is delta ki. If this is Wijk, then this is layer k, and this is layer k minus 1. And so what we're doing is we're multiplying the state from this layer, the one that Wij is attached to, times the delta that's attached on the right. So delta Wij is equal to state from left times delta on the right. Okay, so that's a good way to remember it. And I'm putting a box around it. That must mean it's important. And it is, because now the update rule that we're going to use is that Wijk is equal to Wijk plus alpha times delta Wijk. Good. Now notice that this is a scalar update. We're updating this element by element. Okay, and what we have not proved yet also is that this is actually gradient descent. We'll prove that this is gradient descent. Okay, also we need to determine what happened to the bias terms. Okay, so those are the two things we still need to figure out. Good, but before we do, let's see if we can make this update rule in matrix form instead of scalar or element by element. So how would I make that element or the update rule work? I guess we need to work on this one first. I think you might see it from these two vector or these two elements right here. So let's see, state S in layer k minus 1 has n sub k minus 1 elements to it. And the delta from layer k has n sub k by 1. And what is the size of Wij, or Wk is what size? Okay, you're probably not going to be able to see that very well. It's nk minus 1. Oh, let me write it down here. Maybe I can keep that there. So, just some side or scratch side remarks. So sk minus 1 is nk minus 1 by 1. Delta k is n sub k by 1. And then wk is, I sometimes put these parentheses on, sometimes not, is nk minus 1 by nk. Right, and I know that my update rule is Sj, right, because of that j, I minus 1 times delta, oops, that's a k, k I. Good. You might be guessing what we're going to do. How am I going to get an nk minus 1 by nk matrix out of these two vectors? An outer product. That's right. So the change in wk, layer k, is just going to be delta k transpose. Oops, not transpose. That's going to be the inner product. I need the outer product. S I minus 1 transpose. There we go. That gives me my outer product. And so you might verify that these sizes do match up. That gives me my update rule in terms of the linear algebra. And so in the next video, proof of gradient descent. All right, see you then.